Hi and good afternoon, everybody. Many thanks for joining us today. Today we are talking about steel portal frame building design, and we are talking about using MasterPort to get the most out of your portal frame design. My name is András Hörbé. I'm the sales manager at the MasterSeries. As usual today, I am joined by my colleague P399. Before I start my presentation, I would like to quickly share some practical information about the GoToWebinar tool. The control panel can be hidden with the red arrow button. Questions or messages can be sent with the chat option. Feel free to type in your questions at any time during the webinar, and we will answer them during the session, but we also review the questions at the end of the webinar. As usual, this webinar is being recorded and will be posted to our channels and sent out to your email address. Quickly about the agenda. First, Patrick will overview the anatomy of portal frame design. After that, we will talk about the usual actions on portals. Then he will talk about the structural behavior and stability issues of portal frames, and then Patrick will look through the typical details of portal frame buildings. After that, I will show you how quickly you can design a 2D portal frame using our MasterPort, our portal frame design program, and how easy it is to turn a 2D frame into a 3D frame structure. And as usual, we will finish with a Q&A section. So let me hand over the presentation to Patrick to talk about the background of portal frame building design. So
thanks everyone for coming today. I will be showing you portal frames, and I'll go through a bit of an overview on portal frames, including their advantages, their anatomy, and a bit of analysis and design. I will cover some of the steps within the design process listed here, including geometry actions, frame stability, member verification, and serviceability. I will be assisted with a 3D model here, so if you don't quite follow along with what I'm saying, you'll at least enjoy some of the pretty pictures. And I will be referring to a lot of information as design guidance outlined in various BCSA and SCI publications, specifically P397, P399, and P400. So we'll go to some information taken from the site steelconstruction.info, which is a very useful online encyclopedia for UK steel construction, which is maintained and developed by BCSA, Steel for Life, and the SCI acting in partnership, which I'm sure many of you might already be familiar with. And it states that 50% of constructional steel used in the UK is in portal frame construction, and steel accounts for 90% of the single story market. So it's used a lot. They're very popular and common. And why are portal frames so popular? Well, for many reasons. The portalized frame itself is a highly efficient arrangement relative to its dimensions and the loads it caters for. Steel as a material complements it. Steel has an excellent strength to weight ratio. Portal frames are fairly common and well tested and documented, and therefore have been well optimized over time. And because they allow for a big open empty space, portals can be repurposed fairly easily or extended, so they can be well future-proofed. And because of the efficient design, it is lightweight and it lends itself to minimal foundations. There are quite a few suppliers for proprietary products for portals, and therefore it is also a competitive market. And in my personal experience, some of my first structural projects were for the design of portal frames, and I feel that a good understanding of the basic principles of a portal frame has given me a good platform for understanding the behavior and design of structures in general, as it covers a lot of basic structural engineering fundamentals. We've quite a number on our webinar today, and on recent webinars, we've had some very good input from the participants, and this is a popular topic, so please feel free to add some of your own knowledge, as some elements are outside my own design experience, and it would be good to hear about yours. So onto the arrangement itself. So I've omitted the first gable bay and some of the cladding for this view. So the typical dimensions, the clear span can be between 15 and 50 meters of free open space. which can be extended by multi-bays. A clear height from the top of the floor to the underside of the haunch can be anywhere between 5 and 12 meters. The roof pitch is typically between 5 and 10 degrees. 6 degrees is most common, but I've got 11.5 degrees here shown actually. So, and the frame spacing is typically between 6 and 8 meters. And haunches in the rafters at the eaves are around 10% of the clear span width. So some portal-frame elements. So the portal frame relies on continuity and stiffness through moment-resisting connections in the eaves through the haunch connection, and in the ridge through the apex connection. The main portalized frame arrangement provides the primary method of support for the whole frame through both the vertical loads, which in the green y-axis up and down there, and the lateral loads, so in our red axis, left to right. Our bracing typically provides resistance in the longitudinal direction, so you can see in our blue direction, front to back, and alternatively, we can have a portalized bay or a moment frame incorporated. And if I can zoom in to show that here, hopefully you can see that. But we need to make a note to check deflections on our portalized bay if we're using these, as they're less rigid than a brace bay. We also have secondary steelwork in the form of purlins and side rails which support the building envelope, which is typically cladding. The secondary steelwork transferred all the wind loading from the cladding onto the frame, and we get manufacturer's tables which usually assume the cladding to restrain this secondary steelwork. The cladding protects the building from external elements, and some specialized cladding, I believe, can also act compositely, which I've never actually used myself. So maybe some of the participants can add some light in that. Whether it can be used as a diaphragm in lieu of bracing, I'm not too sure. But onto your gable bay, we have a braced or unbraced gable end bay, depending whether the gable end is a braced simply supported rafter with gable wind posts type arrangement, or whether it is a portalized continuation of the frame. And in many cases, it is portalized for the potential for extending the portal frame in the future. Bracing, we will have roof bracing to transfer wind loads from the gable columns to the eaves, and then back onto the longitudinal bracing, which will carry these loads and more onto the foundations, as well as providing stability for the frames during construction phase. And this bracing is usually located at either or both ends. I have X bracing using angles shown here throughout, but circular hollow sections are common, and flats, but flats are not normally used for the roof as they sag under their own self-weight about the weak axis. So I'll show you some alternative options here. I've added an extra bay on here with a mixture of some of the variations we can have in a portal, which can come in the form of so this is a hit and miss frame. This incorporates multiple span portals, but with a reduced number of columns due to the introduction of a valley beam. This is an economical option where we get a large open space with minimal columns. And I've also included a hip end roof and a parapet at the gable end only there, as you can see, to get an idea of just how they look. Although obviously the parapet would continue around the perimeter of the structure. I've only shown it there at the end. We could have a tied portal frame, which can reduce spread at the eaves level. We could have mezzanine floors for the offices, which is an internal floor, which can be framed out and tied back to the main portal structure using a simple beam and column arrangement, with one of the columns extended up here to show a prop portal frame at the back, which has an internal column which can support the rafter and would just spend the moments in the main frame, but it won't help in resisting lateral loads. I haven't shown other arrangements such as ones which have an overhead traveling crane that can be incorporated and must be considered a part of the primary design, nor mansards, which is sort of an arched portal frame using 4 rafters instead of 2, but this is available within MasterPort. So onto our loads, taking into account a typical frame with standard cladding and dead loads, we can look at our vertical actions and permanent loads. Generally, the self-weight of the roof, secondary steelwork, and the cladding plus services comes in at around 0.3 to 0.5 kilonewtons per meter squared. And for our variable loads, we've got imposed loads, and if they are maintenance only, can be taken at around 0.6 kilonewtons per meter squared. Then we've got snow loads or lateral loads, which are wind loads and maybe crane loads, as well as equivalent horizontal forces which take into account frame imperfections. So snow loads from Eurocode 3 or snow loads are determined by location and altitude from Eurocodes UK National Annex. And there are 3 considerations for the application of snow loads, if I can turn them on and off here. So we've got an undrifted or a uniform snow loads. We've got drifted or asymmetric pattern type snow loading. And then we've got drifted exceptional snow loads. These are considered accidental and more applicable to the design of secondary steelwork. So that gives you an idea of snow loading. So we can look at one loads here as well, and we can talk about combinations with the snow loads in a bit. Wind is a significant factor in the design, and Eurocodes combine wind loads with snow loads, which can create greater bending moments than our combined factored permanent and imposed loads. Therefore, in many cases, it can determine our member sizes and the design of our frame. Our wind loads we can derive from Eurocode 4, again, determined by the National Annex, considering wind velocity, altitude, terrain, distance from the sea, wind direction, and that will help us determine our peak velocity pressure. We can get our external pressure coefficients as well from the same source, and I've shown as an overlay here our external pressure coefficients, and then we can also take our internal pressure coefficients, which is typically plus 0.2 or minus 0.3. And in this case, we actually have a dominant opening here shown at the end, although overlaid by our external wind pressures image. The dominant openings typically considered closed in the event of a storm, but this will require consideration and can contribute to significant uplift in the frame, taking into account its size relative to other openings on other faces. So there are other wind load factors to discuss relative to a portal frame, and to be honest, we could do a full webinar on wind loading alone, but of course MasterSeries wind analysis can take care of all these issues, but it still requires a good fundamental knowledge of wind application from the structural designer. And for combinations, the Eurocode state that gravity actions should be applied together with variant factors, which I've summarized in the list there, considering both wind and snow in combination, switching as our leading variable action. So this can generate quite a few load combinations, again, where MasterSeries can come in handy. So a little bit about our analysis. So elastic plastic design would be the most economical for the design of portal frame, as it considers both elastic analysis, which looks at the frame in the elastic state under our service loads and deflections, and then plastic analysis, which looks for plastic hinges that will develop in the frame under our ultimate loads that will cause collapse. So that's effectively a strength design. And where deflections, i.e. serviceability, govern design, there may be no advantage in actually using plastic design for the ultimate limit state design. If stiffer sections are selected in order to control deflections, it's quite possible that no plastic hinges form and the frame remains elastic at ULS. Our typical elastic analysis bending moment diagram with vertical forces and pin bases is shown here, and we can see the bending moment at the middle of the rafter is close to that at the sagging moment at the ends of the rafter at the location of the haunch. And in our plastic frame analysis, we will get a very similar bending moment diagram, except our ease moment will not be as great because we have hinges formed first at the location of the haunch, and then as a second order effect, load effect increases at the location of the apex, and I'll cover second order effects next. These hinges form at where the cross section locally reaches its plastic moment of resistance, and we'll talk about that as well in our member verification. So I'll just show the bending moment diagram up, and we can see how the frame behaves in the uplift case and how the compression flange flips due to internal pressures, causing the requirement for additional member checks and consideration of our restraint positions and stays for the rafter. Now, I'll talk a little bit about second order effects. So because portal frames are relatively flexible, that means in many cases second order effects need to be assessed, as they can add up to about 15% to your design moments. Second order effects are effects in where there's a subsequent movement of the frame after the initial deflection. Second order effects include those due to imperfections in the portal frame, where we use equivalent horizontal forces, which we mentioned earlier, and imperfections of the portal frame members, again using equivalent horizontal forces. And then we've got flexibility of the frame, which is P delta effects, and then flexibility of the actual members is P small delta effects, and I'll show you that in the next slide as well. The second order deflection is due to the loads changing the initial geometry and therefore the forces within the member. So the process in a typical vertically loaded frame is that the apex drops, we get a plastic hinge forming, and the eave spreading, and then the apex drops further by a small distance, and that's the change. That's our second order effect. So going on to our horizontal deflection slide. So where we have the loads applied horizontally, we get the following deflection diagram where we can see our P delta figures represented. To determine if second order effects may be significant, a frame stability check is carried out to obtain a value called alpha crit, and typically software carries out this calculation, which can then assess whether second order effects are significant enough to cause collapse, or this check can be done manually by an approximation method if the rafter axial loads are not significant. And if you're a MasterSeries user, these checks can be found within the steel design module output. So consideration will need to be given for both gravity and uplift conditions for the columns on the rafter. We'll have major and minor buckling and lateral torsional buckling to be considered along the full length of the portal frame. Plastic hinge locations should be restrained. These are typically at the end of the rafter, at the end of the apex on the rafter, and either at the haunch at the end of the rafter or in the column at the bottom of the haunch. The positions at which a plastic hinge is formed can be managed by the arrangement of the haunches, and at these locations stays should be introduced, as the increased risk of a buckling failure due to the plastic moment resistance being reached at these locations. We will require an additional restraint to the compression flange in the form of a stay. So the columns require restraint at the location of the bottom of the haunch, and thereafter at the end of the apex and at the haunch, as I've mentioned. Uplift restraints, again, we can see the frame and uplift and the flipping of the compression and tension flanges in the rafter and the column. So I'll talk a little bit about some details here, starting with the haunch connection. Our haunch connection increases the bending resistance of the rafter at the location of the highest bending moment in the frame. It increases the stiffness of the frame and therefore reduces deflection, which can often be the governing criteria in our portal frame. And the haunch is usually cut from the same section as the rafter beam, and usually double the rafter beam's depth and about 10% of the span of the frame in length as a rule of thumb. The depth also allows for an efficient bolted moment resistant connection, and as mentioned previously, we will likely have included restraints to the inside flange at the ends of the haunch at the column and rafter. For the apex, we have effectively an angled splice connection. The apex is usually cut from a rolled section and only sized to facilitate a bolted connection, as opposed to resisting any major moments. If you recall from the bending moment diagram, the moments are not significant here. It is not considered in the overall frame stability, but it will contribute to its stiffness. Some typical dimensions are shown here as well. And moment resisting bases are generally unwelcome in the UK due to the complications related to design, increased size and cost, and requirements in most cases for reinforcement. Usually the bases are designed as nominally pinned to allow for the design of members under our ultimate limit design cases, so our 0% fixity. But increased fixity can also be introduced to help with both deflections and frame stability. So if we take 10% when assessing frame stability and 20% when calculating frame deflections, we might get a more realistic value in our deflections. So in both of these conditions, we ignore the moment transfer onto the base. And although not shown here, 4 holding down bolts outside of the extents of the column is common to temporarily keep the column stable during erection. Generally, the only time we may consider moment resisting bases is when we are close to a site boundary and the bases need to be designed to resist overturning in the case of a fire. but this will mean reduced loads, as they'll not be subject to live loads, and in a lot of cases permanent loads will have been destroyed in fire. But further reading is available within the SCI publication P395, which is a fire resistance of design of steel frame buildings. Also to note, horizontal forces on the basis from wind sometimes can be troublesome when you have large wind loads on a lightweight structure, or if the base is kicking out, which is part of the behavior of portal frames. And so relying on passive earth pressure can be unreliable, and the friction from the sliding resistance from the foundations on the soil usually is not enough, and it will require oversized pads to generate enough friction to provide resistance in this case. So we can introduce an alternative option here where we can tie back into the surrounding ground bearing floor slab, utilizing its friction capacity from its own self weight on the ground, or even tying back the full width of the frame to the opposite column. I've shown a rough detail here for tying back into the floor slab using rebar drilled through the web of the column. Details such as this will need coordinated with the floor slab designer and loads specified for the requirement of rebar. Finally, I'll talk a little bit about serviceability issues, specifically deflections, in which many cases will be determined by deflection sensitive details, for example, sheeting or masonry panels. And special attention should be given to the deflection limits and differential deflections between the gable bay and the first adjacent bay beside it, which can be problematic due to the gable stiffness from being typically braced, clad, and the rafters being simply supported. So that's one to pay attention to. So that'll conclude my introduction on portals and some things to be aware of as a structural designer. Our MasterPort module covers a lot more of these issues, and to be honest, I could spend a lot more time on this presentation, but I'll hand you all across to Andras, who will take you through the MasterPort module. So, yep.
Okay, thank you, Patrick. I hope you can hear me and you can see me.
Yep, all good. I hear and see.
Perfect. Okay, thank you. Let me start my software demo with a single 2D bay frame. To save time, I'm going to go through the full design of this 2D frame, but at the end, I will quickly show you how to turn this 2D frame into a 3D building with all of its elements. Okay, so MasterPort is an innovative approach to the generation, analysis, and design of elastic portal frames using the simplified wizard style user interface. We can easily generate of a 2D, 3D portals, including symmetrical and asymmetrical frames, monopitches, mansards, prop frames, and lean-tos. Gravity, wind, and snow, and even crane loads are added as the frame is developed, with ultimate and service load cases being automatically generated. If you wish to make changes outside the scope of this simplified interface editing facilities, then you can switch it off and do manual changes. Okay, let's start our model generation on the General tab, where we can set up the basics for the portal frame. Okay, design code. We're gonna work to Eurocodes 3. By default, the Eurocode will use the equitation of 6.10a and 6.10b to generate the load combinations. You can change this by clicking in the checkbox, so it uses 6.10 instead, should you wish. We are going to pin our basis for design, but in space stability and service loading cases, we will use 10% and 20% base fixities. We will optimize our hunches using the default settings, and we are gonna go for 0.25 kilonewton per square meter dead, 0.6 kilonewton per square meter live, and 0.1 kilonewton per square meter service load. And of course, we are gonna add in the self-weight of the structure. I will put in all the loading cases, and of course we're gonna analyze the elastic critical load factor to see whether or not our frame is sensitive to second order effects, and whether the second order analysis is needed or not. Okay, let's move on to specifying the spans. Okay, putting the model in front here, we can see it is one span now. I'm gonna go with this default one span, and I'm gonna accept the 30-meter span. I'm gonna make the rise to 6.5. As we can see, we have default section and material grade. I'm gonna accept it. I'm gonna accept this for now. Initial cross section, and I accept the default 3-meter Haunch length too. Leaving the Haunch section cell blank will ensure the Haunch assume the same section size as the Rafter. And these are the inputs for apex Haunches, 1 meter long, and the Haunch depth is 2 times the standard cross section depth. And we can also also ask to say yes, we want to a monopitch by putting y here, and the monopitch can be from left, from right as well. Okay, or we can say we want mansard by putting in the length of the mansard, so for example 5 meter. Okay, so that's my span done. Moving across to my columns. The default column height is 7 meters. I'm gonna use this now, and I'm gonna accept the standard cross section and material grades as well. The base fixity setting here is only applicable if the as is option has been selected in the general input tab. Now we are going to pin our bases and use the 10 and 20% fixities for space stability and service cases. So we can delete it or just leave it here. So that's my 2D frame created. I'm gonna add in the wind and the snow load as well by clicking on this button. Let's start with the snow first. As we can see, we're gonna go for a zone number of 0.5 and 100 meters altitude. Based on these two informations, the MasterPort will calculate the various snow loads and load cases. Let's move on to the wind. In the wind, we can put in all the wind pressures and sanctions, or we can use the master key wind analysis module to define all the coefficients and pressure for the various faces of the portal frame based on the selected site location. So let's go and choose a location by click on this edit button, and this is the wind analysis module. So we can pick our site location directly on these maps, or we can use the fast town selector down here, or if we know the exact location of our site, then we can type in the national grid reference number of it. So let's select the city from this drop-down menu. Let's see Birmingham, and let's log the site. Okay. We also need to tell them where the wind blows onto the structure by specifying to the angle to the north. So we can rotate this with, let's say, 60 degrees, and then have the wind blowing there. So that's my wind analysis done. Exit from the wind module. And this already updated all the values based on our wind analysis. By clicking on the wind icon here in the top toolbar, we can see the wind loading on the structure. So this is our current bay. If you want, we can select another bay. We can move this bay. So this is the current. This is the third portal. But if you want, we can calculate the first portal, second portal, and then so on. So this is our current bay, and based on this location, the program will calculate the member forces. Okay, we can select to display the wind coefficients, the pressure values, or even the wind zones. Under the direction drop list, we can choose which wind directions we want to use. The wind load case, the W load cases show the wind for the external pressure only. The P values includes the external and the internal pressure, and the S values includes the internal, includes the external and the internal sanctions. The yellow color, let's go here. So the yellow color represents the wind pressure, the green represents the wind sanction, of course, and the shade of the color depends on the intensity of the actual pressure, if you are on pressure. Okay, so we can now go ahead and analyze this frame very quickly. Initially, we go with the elastic analysis first. And it's ready. So let's check quickly the result in the output. So output, graphical result, and let's check the deflection shape first. So this is our deflection shape. Let's put on some values. So nodal deflections X and Y values, and let's quickly see the result of the different load cases. And let's quickly check the bending moment diagrams, major axis only, and show values. Okay. So we can now see how our frame is currently behaving. All looks sensible. So let's go and do some design. Okay, so steel design. And here we go. So it's showing us our frame and the initial local capacities of the member. First, let's do some auto design. So size as an elastic portal first. Once all the members have been sized, we will perform the plastic analysis. Okay, lightest frame and with normal average restraints location. You can decide whether to have fewer restraints by moving this slide bar to the left. This is giving slightly heavier sections, of course, or use a lighter section available, but possibly more restraints required. So now we go auto size all. Sorry, it's a bit slower than usual, but hopefully it will be ready in a few seconds. Okay. So it's ready. So what we want to do first is to check our space stability. So as you can see now, in some cases, the alpha kit value is below 10, which means our frame is sensitive for the effects of deformed geometry. So we must use the second order analysis. So let's go back to the editing area first. And add the P delta analysis. So let's reanalyze elastic analysis. And still design. And if we check now the space stability, looks good. So we have second order results. Okay, so it's failing. Let's start the detailed design with our column. So let's check first. Let's check and optimize the purlin, the cladding ray position first. So eagle spaced lateral restraints 1400. So let's auto restraint first. The current group. This auto restraint feature takes the specified eagle spacing and tests for failures in each portions. In portions where the restraints are inadequate, their spacing is modified. It also determines the optimum location of torsional stability stays as well, if an appendix BB stability check has been applied to the current group. And this is doing both of the columns as they have been asked to be the same section size, so it is going to assume the same restraints. So it's ready now. So here you can see the portions along the member. So let's check again the appendix BB check. So here you can see the stays. So we have stays here. Let's try to remove this, but no, we definitely need 2 additional stays down the column. Let's go back to the lateral restraint. So you can see here we have the calculated portions, and as you can see, the lateral buckling is the dominant failure mode, but the column works to the Eurocode. Okay, let's quickly see. Let's move on. Move on to the rafters. Okay. The space between the purlins is gonna be 1800. So this is our eagle space. So let's auto restrain it. As you can see, it is running through all the load casings and portions and checks the different stay locations. Okay, and let's see the lateral restraints and the appendix BB. So as we can see, we need to have stays at the normal places. So if you remove this, then you will see that it's not enough. So now it's failing. So we need the 2 stays along the beam. Okay, let's quickly see the design. So this looks good. If you go to the other side, then you will see it's failing. Of course, we have scan for failure substrum. So if you click on it, then the program can quickly run through all the portions and members, and it gives you a warning if any of them is failing. So now you can see we have one failing brief. So if we go back to the section auto size, and if you click on auto size current number, then the program can quickly find us the lightest cross section, because this is what we selected initially. Okay, so that is our simple 2D frame. So this is our frame done. We just need to reanalyze the frame with plastic analysis to confirm that the frame is elastic as intended. So if you click on plastic analysis, you see here, you can see the message that the frame is fully elastic, so it's okay. Run quickly the scan for failures again, just to see that all good. Yeah, we don't have any warnings. Okay, so let's just go out of the steel design and see the rest of the structural options, and see how we can turn this frame into a 3D building. So I close the steel design, and yes, I will illustrate this. So let's go back to the editing area, and let's start on the spans tab. So I'm gonna quickly add additional span by changing this to being 2 spans. As you can see now, we still have only 1 span here in the table. It is because both the in-bay and the global bay symmetry options are being turned on. So I'm gonna turn off the global symmetry to have different spans. I'm gonna make the second span 24 meter, and let's move to the column, back to the columns. And on the column tab, I'm going to make the column 2 to 7 plus 3, which gonna give us a 3 meters rise up on the right hand side of this column. So it is 7 this side and 10 meters on this side, and of course the column 3 will also be 10 meters. So let's see quickly the rest of the options. So we can add lean-tos for both sides if we want. As I add in a new structural part, I get a new tab. So we have now a lean-tos tab. Using the lean-to table, we can define the span of the lean-to, the rise of the rafter, levels of the top and the base of the column, the section size. We can also input dead load, service, and live load, as well as the base fixities and the fixities for the outer and the inner ends of the rafter. And of course, there's an options to have only just lean-to on the left side or the right side. Okay, so let's turn on the lean-to. Oops, there is a problem here. Oh yeah, sorry, I make a mistake. So the column 2 should be 7.3. Okay, it looks much better. Let's see what we also have. So we can also have canopies if we want. We can define canopies for both sides of the structure or one side as well. We can also add in a mezzanine floor. So if I wanted to, I can add a mezzanine floor to span 2 at 3.5 meters, for example. And once I add it in a mezzanine floor, I will need to add in some supporting columns as well. So here we have props. So these are not just for props, but if you turn this on, then we can see that we can move this to the bay 2. If you go back to the mezzanine, then we can give this remove part back, middle section back. Okay, I'm gonna drop out this mezzanine to keep our design clean and simple. And also I will remove the props. So let's turn this 2D frame into 3D structure by clicking on this button, this 3D button. So on the 3D tab, here we can define the base spacing and the other global parameter. So I'm gonna say I want 8 base, and the spacing, let's say, will be 6.5. Okay. Okay, as you can see, we have 2 extra tabs here. So when I click on the generate 3D frame, the gable and the bracing tabs are automatically activated. So what I'm gonna do is go to my gable post. So we have 3 sets of posts, and remember the in-bay symmetry is still turned on. So that's why just the half is defined. So we have a gable 5 meter, 10 meter, and 15 meter in the middle in the span span 1. So let's put in some post into the other bay. So I need to say, okay, this post will go to the bay 2, and by typing 6 meter here and 12 here, we can specify our gables in the span 2, the bay 2. So we need to change our bracings to match that. To do this, I go to the bracing tab, and as you can see, at the minute, it is thinking that we have 6 legs in the roof bracing, which is good for the bay 1, but for the bay 2, I will say I need 4 legs only. If you want, you can use X bracing as well by typing X here. Yes, or we can go back to normal bracing. Okay. So as we can see, we have 2 legs both in the internal and the external wall bracing, which makes sense for the external bracing. However, for the internal bracing, the rise doesn't look nice. So I'm gonna change this internal bracing legs to 3, and I'm gonna move this point up to here. To do this, we need to turn off this dynamic bracing generation option. And if we click on the button, click on the member, then you can see that the program automatically find me the proper positions. So let's say it's gonna, sorry, what's going on? So it's gonna be 7, and this is gonna be 7 as well. And if you want, we can move down this other end to move to 3.5 meter, and again 3.5 meter, and that's it. Oops, I lost my ties, so let's go back to the dynamic menu to get back these ties and try again. So it will be 7, 7, and Y2 will be 3.5 and 3.5. Okay, so all looks good. So we have You have a nice 3D frames with all the bracings and gable post and so on. So that is the portal frame design using the MasterPort. The last thing what I'd like to do is just to thank everyone to attending today. I hope you enjoyed and learned in this presentation, and see you on our next webinar. If you have any questions, you can get in touch with us on our usual channel. If you want to try out of the software, just go to the MasterSeries website and fill in the requirements form to do so. After the webinar, please do not forget to fill in the short 1-minute survey to let us know how you like the webinar. So ladies and gentlemen, thank you very much and goodbye.